Right. So if the molten or unmolten particles, they are impurities. If they are impurities, it means foreign elements. Then we call the nucleation is called heterogeneous nucleation. Okay. And if they are of the material itself, जो material melt हुआ है, उसी का अगर कोई particle है, then we call that to be a homogeneous. Now let us look at a video. I think it will be clear to you.
Metals is usually in the liquid state. From there, the metal is poured and solidifies. In the process, the microstructure is formed. The conditions that must be met for such a solidification to take place are explained in more detail in this video. In the liquid state, the metal atoms are distributed in a completely random manner. Due to the high temperature, the atoms have a relatively high kinetic energy. In this state, the attractive forces between the atoms are not sufficient to bind them together permanently. Heavy collisions with other atoms cause any bonds that may have existed for a short time to be broken again immediately. When the melt is now cooled, the kinetic energy of the particles decreases as the temperature drops. When the temperature falls below a critical point, the mutual attraction of the particles becomes dominant. The bonds between the atoms can now become permanent. In this state, the solidification temperature has been undershot and the actual solidification process begins. Solidification usually occurs simultaneously at many points in the melt. In this way, many small grains are formed from the melt. Although each grain has the same lattice structure, this is spatially oriented differently from grain to grain. Due to the acting attractive forces, more and more particles from the melt now attach themselves to the already solidified lattice structure. This process continues until finally all particles have joined the metal lattice and the grains touch each other. The microstructure has now completely formed. Since the crystal structure of the metal is formed during this solidification process, it is also referred to as crystallization. The temperature.
Okay, so this is how it is taking place. Now, this is actually a first order phase transition. So, यहाँ पे again the Gibbs free energy change is very important. Okay. This Gibbs free energy change, delta G, during the nucleation and growth process, it has got two contributions. One is volume, and one is surface. Volume is simply 4/3 pi r cube delta GB. Actually, as an infinite capacity, volume contribution. And this is the surface. Contribution. This is the volume contribution, 4/3 pi r square is the volume into delta G plus 4 pi r square gamma. This is the surface tension or surface energy. Now, for the Gibbs free energy और जहाँ पे Gibbs free energy change होता है, that is actually a maximum. That means if you plot delta G with respect to say nucleation distance R, really these are maximum. Maximum. And this point जो this radius, this is R star, this is called a critical radius. So यहाँ से you can actually find the critical radius. You can, if you plot, if you have D delta GD by dr is equal to 0. Okay. From this arch, critical radius. I'm just coming into that. Critical radius is the radius where when the nucleation is taking place, there is a formation of an embryo. जैसे biology में तुम लोगों ने पढ़ा होगा, उसी तरह से similarly this embryo or the small viscera is taking place. Now, if the radius of the embryo is greater than R star, critical radius, only then the homogeneity or the nucleation will proceed. If it is less than this, if R is less than R star, then the atoms will again melt and go into the working state. So, it denotes this maximum value of delta G. Okay. Right. So if you just solve this, you get. I'm just writing the expression. This GR star R star comes as minus 2 by delta GD. And corresponding, you can, if you put the value of this R star into the expression, you will get the value of delta G star. ठीक है, so I think I should stop here because I'm getting called by a lot of people. So I will stop here and I will continue this in my next class.